So, revision, lecture, chapters 1 to 5. Well, the good news is there's no material in chapter 1 you need to remember, unless you want information about how this course is run, and I guess the assessment strategy is described in chapter 1. But there's no dynamics content in chapter 1. So chapter 2. Chapter 2 was entitled The Basics for Single Degree of Freedom Systems. And some of it will have been revision for you guys. Okay? But I started off with the absolute basics. Talked about undamped systems. Okay? So that's systems with no damping, there's no C term, and there's two solutions. There's one for free oscillation, okay, where there's no force being applied to the system. You just hit it, let it go of its own accord, okay, and you get a solution. The solution, as you can imagine, might be a sinusoidal, okay. So there's a cosine in there at a certain frequency, which happens to be the system's natural frequency, okay. It's got a certain amplitude, that depends on how hard you've hit it in the first place, and then the phi term at the end accommodates for where along the cycle it started oscillating, okay? And that's the solution. A and phi in that situation will be defined by the initial conditions, okay? So if you've been given initial conditions and you know it's a free oscillation, undamped, you can apply that to that equation and you'll get the solution, the complete solution, okay? You find x of t, you find x dot of t, because your initial conditions, you obviously need two of them to find the two unknowns. And you'll end up with two equations, two unknowns you can solve for a and phi. Okay. That's a free oscillation. If you've got a forced situation, in this case a sinusoidal forcing function, for an undamped system, you're going to get this as your response. And notice that in this case, A is defined entirely by the force that's being applied. Okay? That omega there is not omega naught, it's omega. Okay? There's no omega naught in this solution. And F naught is the amplitude of the sinusoid that you're applying. Okay? Well, that's forced oscillation. More details can be found in the notes. For damped systems, you slowly introduce damping. So for free oscillation, we've got something very similar to that. For free damped situation, it's very similar to the undamped case. Excuse me. Very similar to the undamped case, except you've got an omega d, which is your damped natural frequency. Okay, and you've got this exponential term, this decaying exponential. E to the minus something times by time is a decaying exponential. So as time increases from 0 to infinity, this term gets smaller and smaller and smaller. Okay, and when time goes to infinity, that term is then falls 0. That makes sense. If you've got a damped system and you set it oscillating, you let go, it's going to oscillate, but the amplitudes are going to reduce and reduce and reduce until it stops. This is more like a real system. Okay. We've got natural frequency featuring in here. We've also got this term zeta, which is the damping ratio. Again, well, I'll go through what's on the equation sheet in a minute. But you can find equations for those things and damped natural frequency. Again, with this situation, there should be an equal sign here, by the way. In this situation, A and alpha are determined from your natural frequency, your natural initial conditions. A and alpha are determined from your initial conditions. Okay, so again, you'll be given what's happening when t equals 0 in terms of displacement and velocity. You use the displacement equation here. You take the derivative of this equation with respect to time to get the velocity equation. You apply those initial conditions, two equations, two unknowns, you'll find A and alpha. With forced oscillation, this is known as the steady state solution. You end up with this equation, okay, where A and delta are explicitly defined by the forcing function that's being applied and characteristics of the system. Okay. A and delta are explicitly defined. Because this, essentially this system, it's called the steady state solution because it's as time goes to infinity, the thing will essentially be oscillating at the frequency at which you're driving it. Okay. Whether there's damping or not is sort of almost immaterial. There's no damping featured in here. Okay. as time goes to infinity, the system will end up oscillating following that sinusoid, which is what you're applying to the system. So looking at each of these sections in a bit more detail, this is actually from the formula sheet. Okay, so for the undamped free oscillation, you've got your equation of motion at the top, mx double dot plus kx equals 0. The solution, the first one is the one I've just shown you, a cosine omega naught t plus phi. Okay. As I said, a and phi are determined from initial conditions. You can also write this equation in this form. Okay, we went through in the notes how to go from that form to that form and back, vice versa. Okay, there's some terms A1 and A2, which you can stick in here, and if you ran through the equations, you end up getting the same thing. Okay, but like I said, A1 and A2 are dependent upon A and phi are determined from initial conditions. So there's your solution. If you know the initial conditions, there is a quick way straight to the solution, which is following this format here. So if you know your x at time equals 0 and your x dot at time equals 0, you can plug it into that solution and you'll get a solution straight away. Okay? So you don't even need to run through getting the derivative of this equation and all that sort of stuff. You can actually just use that solution straight up. That's on the formula sheet. Okay? So you're given initial conditions, you can actually just plug it in and you'll get your answer. Undamped forced, well there's the equation of motion, and you can see it's a sinusoidal forcing function where omega is the driving frequency that you impose on the system. It's not the natural frequency. Okay? There's no subscript naught here or subscript n, it is simply omega that you are giving to the system by the forcing function. Okay? And then there is the solution, which we've just seen. If you've got damping, like I said, there's a few terms that we need to think about. There's this thing called damping ratio, which is the damping that's actually applied to the system divided by what's known as critical damping, the damping that gives you this critical, and obviously if your damping equals that, you get a damping ratio of 1. Okay. Generally, systems will not be underdamped, so C will be less than 2 root mk. Okay, you'll get an oscillation, and that's what happens in most real-life systems. It's not overdamped. Okay, and if you've got an underdamped system, then you'll have a natural frequency omega d, which will be less than omega naught by a little bit, dependent upon your damping ratio. Okay. Loss angle. You may come across this in questions, certainly some of the revision stuff. Loss angle is simply another way of talking about the damping, and the angle it will be given by this term that is called delta here. Don't confuse this delta with the delta that we talk about in the forced damped case. Okay, but if you've been given loss angle, you plug it into this equation, you'll get zeta. Okay, if for these two, if there's no driving function, okay, then this term becomes 1. Okay, so you don't need to worry about it. It's just 1/2 tan delta approximately equals zeta. Okay, and the other way of writing that is tan delta. If you run through the equations here, you can end up getting this as your solution. So again, if you've been given a loss angle and you know the spring stiffness, you know the natural frequency, you can find C. Okay. So that's the relationship between delta and zeta, and that's the relationship between delta and C. Okay. And the other thing that we talked about briefly was the fact that when you have an oscillation that's damped, the amplitudes will decrease in amplitude. Okay, and this equation here will govern how it decreases. It's an exponentially decaying function. Okay, and that lambda is what determines how quickly it decreases down. You can see that's a function of zeta. Okay, so a function of your damping ratio. And so let's assume n is 1, so I'm talking about one amplitude and its following amplitude. One amplitude, A1 or A5 or whatever, and AI plus 1, 5 plus 1 or 6. Okay. The difference between those two will be governed by that equation. Okay. So with damped free oscillation, so this is our equation of motion, it's free, which means there's no forcing function here. That is one form of the solutions. And you can also write that equation as this equation. Okay, so they're both valid. And the relationships between A and alpha and A1 and A2 are given here. Again, this is from the formula sheet. Okay, and again, A and alpha and A1 and A2 are determined from your initial conditions. Okay, so you can go through the process if you want to, or you can use this equation at the bottom. Okay, this equation, you've got x naught, which is your displacement at time equals 0, x dot naught, which is your velocity at time equals 0, and you basically plug in the values and you'll get a solution. Okay, again, that's on the formula sheet, you don't need to remember it. So if you know your system is free but damped, okay, and you've got initial conditions, you can plug the numbers in, out pop your solution. When you've got forced oscillation, it gets a bit more complicated. There's our equation of motion. We've got a sinusoidal forcing function. Our solution will look something like this, where A and delta are defined explicitly, and A and delta are defined here, and delta is here. Okay. R is what's known as the frequency ratio, okay, which is omega divided by omega naught. So obviously when R equals 1, you know you're at the natural frequency. Okay, and yeah, there we go. And here we've got M defined in this graph, okay, which is known as the amplitude ratio. When M is F naught upon K, it's known as the static displacement, okay, and sorry, when M is 1, you're at the static displacement, F naught upon K, okay, and obviously M will change depending on where, you know, your frequency ratio. So the graphs down here show what happens to the amplitude as your driving frequency omega goes up. Okay, so as it goes up, it hits the natural frequency where you'll find a peak. The height of that peak will depend upon your damping. Okay, remember we talked about quality of oscillation, Q. If you've got a high quality oscillator, there's very low damping, and you can see as you get very low damping, you get a peak that tends towards infinity. Okay, but if you increase the damping, obviously you get that peak is attenuated somewhat. And delta is like I said, it's a phase. It's a minus sign, so this is minus phi. You start at 0, you get to the natural frequency, you'll be half a pi away from, you know, behind your driving frequency, so 90 degrees, okay? And as you tend towards a much, much higher frequency, you'll be up here at minus pi, okay, so you'll be 180 degrees behind the phase. So although your system might be driving this way, the response is actually in the opposite direction, okay? And you get this sort of oscillation going on. So it's worth remembering these sort of, you know, what tends to happen, okay, based on this stuff here. So remember, R is omega divided by omega naught, and M is your amplitude divided by F naught upon K. With F naught upon K on its own is known as the static displacement. Okay. Right, so that's chapter 2. Chapter 3 was all about forced oscillation and looking at not only the steady state solution as time goes to infinity, but the whole solution from time equals 0. Okay. The full solution comprises two parts. Okay. The first part is known as the complementary function. The second part is known as the particular integral. The complementary function is simply the solution to free oscillation. Okay, so you take, we saw in the on the slides, go back. If you're damped, that's your complementary function. Okay, and if you're undamped, then that is your complementary function. Okay, it's very straightforward. You just take the solution for free oscillation. The particular integral is a bit more challenging because it depends on the forcing function. Okay, and the process that you go through is you take a trial function that is in the same form as the forcing function. So if your forcing function is a linearly increasing force, then you take a polynomial. If it's a sinusoid, you take a sinusoid. If it's an exponential, you take an exponential, and so on. As long as it matches up with the same form as the force, you should be able to go through the process and solve for it. Okay, but there'll be some unknowns in that trial function. There's a table in your notes with sort of example trial functions. Okay, and I suggest you perhaps, certainly be familiar with how it works. There's an unknown in that trial function, or unknowns, and when you solve for it, you'll get those unknowns. Okay. When you plug it in to your equation of motion, okay, xpi goes into your equation of motion, you should be able to sort out what those unknowns are. That will give you a general solution. Okay, if you just plug those two things in, that will be a general solution. There will still be unknowns in the equation, okay, because you've got unknowns in your free oscillation, okay. So you have to go back to initial conditions to determine what the exact solution is for your particular case. Those initial conditions may be the rest conditions, but you don't know that, okay. You'll be told that if that's the case. The equation sheet lists every general solution, both damped and undamped, for a rectangular step function, a linear increasing forcing function, exponentially decaying force, and a sinusoidal excitation. So here's the under solutions. Okay, you've got undamped and damped equations. F of t will be a certain type of forcing function. And you can see on the both sides, you see we've got the general solution. So there's the case where you've got a step forcing function for the, and there's the same equation for the damped case. Notice the difference down here. You've got a decaying exponential and omega d instead of omega naught. Okay. Linear increasing function force, again, you've got both solutions. Okay, so the difference is that these terms will change. Okay. And then an exponentially decaying force, you've got more terms in there, and a sinusoidal excitation. Now for the exact solutions, like what I've also provided you is when the system is initially at rest, I've given you the exact solution. So here we've got a rectangular step forcing function. That is the exact solution when x of 0 is 0 and x dot of 0 is 0. Okay, so I've applied those initial conditions to the equation above and solved for it and given you that answer. Okay, so you don't have to go through working out these equations. And again, that's just for the undamped case. The reason I'm not giving you for the damped case, you can do it, okay, but often the equation would have been too long to fit on the piece of paper. So I thought, well, that could be an interesting challenge for you if you decided that it was necessary to solve. Okay, so there's the so that's what's provided to support chapter 3. Like I said, I've given you the exact solution for undamped cases with initial rest conditions. The work we covered in chapter 3 was very much to support the work from other chapters. Okay, we use it in the following chapter, in chapter 4, the forced oscillation stuff. And you also remember you used it when we were dealing with modal analysis, because often the solution that you found for modal analysis matched up with the solutions we found in chapter 3. Okay, so you could just take those equations, the ones I've provided you on the formula sheet, and apply them to the stuff with modal analysis to solve for that modal equation. Chapter 4 was all about forced periodic oscillation, periodic being the key word here, because we can use Fourier series to find a solution for those periodic forces. So here we're not talking about sinusoids, okay, that is indeed a periodic force, but we're talking about non-sinusoidal periodic forces, so like square waves or triangular waves or sawtooth waves, these sort of things. And they can be represented by a Fourier series, which is given by these equations. Okay, it is a sum of sinusoids of a sinusoid of certain amplitudes, okay, and the amplitudes are given by AN and BN, and depending on whether your system is odd or even or neither, okay, you can obviously make assumptions about the value for AN and BN, depending on that, okay. This is the case for a general period. If you wanted to do it in frequency, you could obviously apply T equals 2 pi divided by omega in there, and you change the equation, but it would be exactly the same as what we've got here, okay? or t equals 2l, again you could change the form and it would be exactly the same. So this is what's provided on the formula sheet in terms of the Fourier series, okay? And you can see that's the equation that we were using. Now how does this work with dynamic systems? Well, there's a process, a three-step process you can go through. First off, if you haven't been given it, you need to find the Fourier series of that forcing function, okay? Depending on what that might be. It might be a square wave, it might be a triangular wave, or whatever. You'll be given enough data to work out the Fourier series of that, okay? And you apply the mathematical theory behind Fourier series. That's the first step. The second step is to solve. Notice that without a constant term, which is what we've got up here, there's a number of different Fn terms, which is representing one of those particular nth harmonic frequency forcing functions. For each of those, you can solve for x. Okay, so you've got your equation mx double dot plus cx dot plus kx equals f. Okay. Well, for the nth harmonic, you can solve for the nth x. You solve each of those. Okay. Often you can solve them all in one go as a sum, in a sense. Okay. And if you go through the example that we did in the notes, you'll see the way I've solved it all in one go. I've just left the n in there. So essentially, for each of these, you need to solve for one of these. Okay. For each Fn, you solve for x of n. And then the solution is simply adding all those xn's up together. So again, you end up with a sum, which gives you x of t. That is the process to solve for periodic problems with a Fourier series. And there is an example problem on page 163 that goes through the process for a square wave. We go through step 1, which is obtaining the Fourier series. For that's the square wave. We end up with an equation with a sum in it. We then solve the differential equation for every n that you can think of, okay, from 0 to up to infinity. Okay, we solve for that, we get a value for x of n, and then we add up all those x of n's down here in the last step to get a solution for any time. Chapter 5, we moved on and we talked about 2 and 3 degree of freedom systems. Okay? And to solve these problems, there's 3 general steps. Okay? And this ties in very well with the modal analysis stuff, which is steps 4 to 8, to get a complete solution when you've got a forcing function. Here we're talking about free systems. Okay? The first step is you find the equation of motion, and there's 2 methods you could do that. You could do the slow way, which is to draw free body diagrams, apply Newton's second law, rearrange, etc., and then stick into matrices by writing the equations in a certain way and then joining them up together. That's the slow method. The quick method is to just use the quick method that we talked about in the notes. Just by looking at the picture, okay, you should be able to go from the picture to the matrix form of the equations of motion in one step, okay, by following the method detailed in the notes. I don't mind which method you use, it's up to you, okay. If you can't remember the quick method, then do the slow method, okay. You'll get the same result. The next thing you need to do is you need to make a substitution, okay. The substitution can be in this form. The other form might be involving the exponential, remembering that the real part of e to the j omega t is going to be a sinusoid with frequency omega and time being t. So you could apply the substitution, okay, and that will give you the mechanical impedance matrix for your system, okay, which will be a matrix multiplied by x to give you equaling 0. And that matrix, if you find the determinant of that, you'll end up with an equation, a characteristic equation, which will be probably a quadratic if you've got 2 degrees of freedom. And those, if you solve for that quadratic using a quadratic formula, you'll end up with 2 natural frequencies. And then what you do is you go back to that equation with the mechanical impedance matrix in it, you insert those natural frequencies in, and you'll get your mode shapes. Okay. Generally, if you've got 2 degrees of freedom, you'll have 2 natural frequencies and 2 mode shapes. 3 degrees of freedom, 3 natural frequencies and 3 mode shapes, okay, and so on. If you've got a system that's semi-definite, it means that there are no masses or springs connecting the system to ground, okay? It's free, it's floating around. It's also called degenerate, or it's called a floating system. For 2 degrees of freedom, if you had 2 degrees of freedom, semi-definite system, there'll be 1 natural frequency, because the other one is 0, okay? And there'll be one of the modes will be 1 and 1, okay? The system is not oscillating, it is merely floating around, okay? Without any oscillation. The other mode will obviously be oscillating backwards and forwards. It could be floating around at the same time, but there'll be an oscillation going on. And you use the same method for grounded systems to find the other natural frequency and that mode shape, okay? It's exactly the same process as you've got a 3 degree of freedom system, okay? In the grounded case, you'll end up with a cubic that's very difficult to solve by hand. If it's semi-definite, you know one of those omegas in that cubic equation will end up being 0, so you can solve it like a quadratic. Okay? Same process for 3 degrees of freedom. The equation for a determinant of a 3 by 3 is given on your formula sheet. Okay? It's up there, clear for you to see.